Systems in the Technical University of Athens, and it's ICCS also coordinates PoDIUM. I will be moderating the webinar for today. So before we get started, I just want to inform you that throughout the presentations, you will have the opportunity to submit your questions to the Q&A box that you can find on your control panel. However, we will be taking them all at one time at the end of the webinar. We'll have reserved 10 minutes for that. And now for introducing the agenda, the presentations, I would like to ask all speakers to turn on their cameras. Great. Thank you all. Thank you all for being here. So our first speaker for today is PoDIUM's project manager and my colleague, ICCS colleague, Lazaros Katzikis, who will be giving us today a short introduction to the project and its objectives. Next, we have with us today Michael Buchholz. He's the head of the research groups for electric mobility, but also connected driving and connected infrastructure at Ulm University in Germany. Michael will be providing us with an overview of the PoDIUM's platform architecture before we go into details and delve into its different components. Then we have with us Amr Risk, who is a professor and head of the Networks and Communication Systems Lab at the University of Duisburg-Essen, who will be presenting the PoDIUM's communication view. We also have with us today Jorge Suarez Luque from ETRA IND, who will be taking us through the functional view as well as the data flow in the platform's data flow. And last but certainly not least, we have with us Guido Gavilanes. He's a senior researcher at the Links Foundation in Italy. And he will be closing the webinar with a presentation on the data truthfulness and software integrity for ITS. Thank you all for being here and looking forward to seeing all your presentations. And I wouldn't want to take any more of your time. So Lazare, the floor is all yours.
Hello all. Thanks, Evie, for the introduction. I will be starting with the general presentation of PoDIUM, the project itself. The project has started in October 2022, and it consists of 26 partners. It is part of the CL5 Horizon Europe call. And it involves, as you can see, roughly half of Europe, 8 countries, and has a total budget of 12 million euros. We started in October 2022, and we will be running for 3 years in total up to 2025. So getting into the details of the scope of the project aims ultimately to enable connected and cooperative automated mobility in real traffic conditions. And to achieve this, the consortium has realized that certain aspects need to be addressed and developed further. And this constitutes in advancing multi-access edge computing, known as MEC, to enable the advanced use cases envisioned in the project, to enhance how data fusion from multiple sources can be achieved to build enhanced environmental models with the ultimate goal of advancing towards digital twins, and extend CITS messages to achieve these goals. An horizontal activity that has been recognized by the consortium as critical for the success of our ambitious goals is to ensure software integrity, trust, and truthfulness of the CCAM data, and to integrate the vulnerable road users into the whole picture of CCAM. In the end, the project aims to demonstrate all the advancements and the real operation of the PoDIUM system in 3 living labs in covering both urban and highway use cases. The 3 living labs capture all the possible connectivity options, ranging from 5G standalone testbeds in FR1, traditional long-range cellular communications, up to millimeter wave, ITS-G5, and even 60 gigahertz Wi-Fi. Overall, we expect that the project will be touching all the entities of the physical and the digital world of CCAM, ranging from mobile multi-access edge computing, wireless networking aspects, and all the entities on all layers of the system, as shown in this picture here, ranging from the road level system part to the edge layer that enables low latency and processing closer to the user, up to the central cloud. I won't get into the details of the architecture. I will just mention that we have this orthogonal activity of software integrity and platform services that we will be seeing in the next presentations. Moving on to what how the project is running and is going to be implementing the developments proposed. We have organized the work in 3 living labs, one in Spain, one in Italy, and one in Germany. And we have some common aspects in all LS, and this is that all are utilizing MEC, which we consider critical for the support of the advanced CCAM use cases. We have always, we're always relying on cellular communications because this provides the extended coverage needed. But we are also enabling and utilizing ITS-G5 for local communications, especially short-range ones. All the scenarios involve connected automated vehicles and also mobile devices as VRUs. Now, getting a bit more into the details of its living lab and the use case, I will emphasize a bit some certain aspects that are of interest and what its use case and living lab is focusing on. So in Germany, we have an urban T-junction, which is shown here and is fully equipped with all the necessary communication and infrastructure gear to support advanced use cases. And in particular, we have aspects related to enhanced connectivity and multipath connectivity that are being addressed in this site. Then in Spain, we have 2 different scenarios. One is about urban traffic, a corridor in the city of Barcelona, which will be utilized by emergency vehicles communicating with and being prioritized by the emergency management center. Traffic light controllers are also into the game. Then the second use case that we're focusing on in Spain is a cross-border corridor between Spain and France, where we are operating a connected automated shuttle crossing this border. Last but not least, we have the living lab in Italy with 2 use cases. An urban intersection in the city of Turin, where we have a team assisting with its edge infrastructure, which is close to real commercial use case. And we have a highway tunnel located on the Autostrada del Brennero, where we have RSUs assisting the operation of the tunnel throughout end-to-end. And the special aspect that the living lab in Italy has is what we mentioned. It is focusing a lot on how we ensure software integrity, trust, and truthfulness, as the presentation of links will be showing later on. And now, what we aim to achieve through PoDIUM after the 3 years of intensive work planned is that in the end, we aim to have an enhanced blueprint for CCAM services, indicating how tightly integrated physical and digital infrastructure can provide what we call digital twins. The second main objective is that we are targeting to enhance the quality and the trust that we have on the external data that we're collecting from the multiple sources available in the PDI of CCAM. We will be demonstrating also the potential and feasibility of multi-connectivity using multiple alternative technologies and multiple paths for enhancing reliability and latency of CCAM services. And in a broader scope, these advancements, in the end, we hope that will support the vision of the European Union of low carbon and more energy efficient transport with increased safety, and will eventually lead to increased uptake of the CCAM related systems in the real world once we will have succeeded demonstrating in real life that the scenarios considered are working and improving the current state of the art. So that's all from my side. Thank you. And I will be giving now the stage to Michael to go on with the details of the architecture proposed by PoDIUM. Thank you.
Thank you, Lazarus, and I hope you can see my screen now.
Yes.
I want to start from that figure that Lazarus already shortly showed, which summarizes the overall PoDIUM platform architecture. It's based on earlier physical and digital infrastructure reference architectures, for example, from the ICT for Card projects, but also others. It comprises C-roads aspects and so on. And we did several extensions because they are needed by our use cases and in the living labs that we want to show. For example, a hybrid data management, especially the multi-connectivity. That's one of the points we are focusing on today in today's webinar. That's also already mentioned, the integration of VRUs and the calculation of digital twins, but also cooperative services and the horizontal software integrity and trust mechanisms you will hear later on by Guido. To handle this architecture, because I mean, such a picture is not detailed enough to present all aspects, we derived 5 different views, and each of the views focuses on different aspects and is meant for the respective experts of the area, for example, a communication view or a data flow view and so on. And I will just give a short overview so that you see how those different views and the different aspects and entities in the system are linked together. And you will get to know about the details in the later talks of my colleagues. The communication architecture, as we have already heard, combines several different communication, let's say, communication means. On the one hand, the ad hoc networks like a 60 gigahertz Wi-Fi, which should be investigated if that's useful for CCAM services as well. The quite common ITSG5, also Wi-Fi technology, but on the other hand, also cellular mobile networks. And Lazarus also already mentioned that we have the let's say normal centimeter wave parts, and we will newly inspect also on the millimeter wave parts. Also, the sidelink communication between vehicle to vehicle will be, or vehicle to roadside units will be researched on and presented in the living labs in the end. And for sure, we have some wired connections to connect the roadside units with a server, for example. And it's not only about bandwidth, the multi-connectivity approach we are addressing here, or integrating end users with different communication technologies, but it's also on enhancing reliability. So we are implementing a system that allows to choose the most reliable communication path for urgent or messages, for example, and also to prioritize. You will hear a little bit more about that by Amro later in the communication talk. Then we have different function blocks. That's important for the living labs to present their scenarios and use cases. And this is only a rough summary of all the functional blocks. There are in the detailed view, you will have much more details, which split those big boxes into smaller ones. One of the main boxes, one of the main aspects in the project, which is also common for all the living labs, is that we will in the end have a digital twin of the traffic going on in the respective area of the pilot and scenarios. We will have cooperative services that can either be a cooperative traffic management, like we've heard for the emergency vehicle, for example, or on the other hand, really proposing maneuvers to connected road users like automated vehicles, but also human-driven vehicles or even vulnerable road users that are connected. It will also include a risk management so that we can warn users based on this digital twin, for example, that a possible accident could happen if they just go on like they do at the moment. And then the horizontal part that we will have software integrity insurance on all the different levels of the platform. We have already seen the cloud, the edge, and the road user level. The generic interface between the different actors in the system, and sensors, so on the roadside level to the edge or cloud level, are the CITS messages, which allow for standardized communication. And those messages are also a main aspect of the data flow architecture, which is very complicated, as you can see here. And that's just the generic overview. So that's the simple figure of it. Jorge will explain to us the data flow later in more detail. I think the main message to link it with the others is, on the one hand, this data flow should be possible on all the different communication channels, no matter if it's an ad hoc network, if it's wired, or if it's a cellular network. And on the other hand, we already know, or we have already seen during the proposal phase and the preparation of the work until this architecture, that not all the aspects we want to realize in our CCAM services in this project are already sufficiently covered by the existing ETSI messages. So there will be also some input from the new functionalities to the respective standardization working groups through the different partners involved in those activities. We have already talked about different entities, and from a first place, we had a look from the physical part, we experience road traffic on the road. So we had the road level and the edge level, but there's also computing entities in the background. So you have computing entities in the vehicle, or even in a vulnerable road user has one if he or she has a smartphone, for example. The cameras have computing entities, but we also have for sure large computing power on the edge and the cloud level. And the overall architecture is meant to be flexible so that also deployment can be shifted between the different levels wherever it's necessary. So that same services can be reused and shifted in this deployment structure. And this is part of the IT environment architecture. Finally, we have the software integrity architecture. This is also only the overview picture. Guido will tell us a little bit more about that in the last talk of this webinar. And it's meant to integrate the trust in either the computing entities of the system. So that's like trusted platform modules, also the software which runs on those computers, so that we can ensure that the software is still the software module we intend to run on that computer, and it has not yet been modified. But on the other hand, we also want to work on the trust in the data, and that we ensure that the data that we process is still useful for the cooperative services. That's a second aspect of this software integrity and truthfulness, data truthfulness part of the architecture. Yeah, that's just the kind of like a broad picture with the different views on overall architecture. And now I hand back to Sevi. I think Amre is, or directly to Amre. I think he's taking over. Oh, sorry, the data truthfulness. It's another picture. I already talked about it, but now I will hand over to Amre, and he will talk a little bit more in detail about the communication architecture.
All right, thank you, Michael. I hope everyone can see my screen now. Yes, great. All right, so I'm happy to take over this part, introducing a little bit more in detail our communication view in PoDIUM. My name is Amarisk, and let me start with the communication architecture that Michael Buchholz just showed. As you can see, our overall architecture comprises integration of mobile road users and roadside equipment via different communication technologies that I'm going to be talking in a minute about. And one point which is especially interesting in the context of PoDIUM is the availability of multiple communication technologies and a new concept that we denote communication types, which makes a flexible use of the different communication technologies that are available. The idea behind this is, as mentioned already by Michael and by Lazaros, not just latency, but reliability. So we would like to understand the impact of using different communication types that are orthogonal to the different communication technologies that are available in enhancing or reducing latency and enhancing reliability. Now, let me show you a more detailed view of the communication architecture. There you can see on the left what we denote as levels of communication, that is either a road level system or on the edge level or edge layer together with the cloud layer. You can see on the right-hand side the different communication technologies that are available in PoDIUM. To be very specific, we will have cellular communication, either centimeter wave or millimeter wave, both 5G communication. You can see the types of ad hoc communications that we have. That is local communication, either using 60 gigahertz Wi-Fi or ITS-G5 802.11, basically 802.11p, or sidelink, as also known as PC5. And from the different coloring of the arrows, what we see, the types of the arrows, this is basically the concept, or behind this is the concept of the different types of communication, that is the combinations of different types of technologies within a point-to-point or a point-to-multipoint communication. I will get into this in a minute. So this gives us the segregation of the communication view into levels, into technologies and types of communication. Now, speaking first about levels, you can see that we have on the road level the devices that participate into the communication architecture, that is user equipment, basically using only centimeter wave communication. We have optional millimeter wave that is together with centimeter wave supported on onboard units. These onboard units are the ones that you see here, for example, in the context of connected vehicles or connected automated vehicles. And we also have an infrastructure that consists of sensor processing units, SPUs, and these SPUs are also able to communicate, as you can see here in the architecture, together with basically a cloud layer. One such SPU, you see it here, a figure out of the road cross T-junction in Ulm, how it actually looks like with all the sensory and also communication infrastructure that is connected to it. We have on the other hand, in the cloud, respectively, edge layer, we have multi-access edge computing, which provides compute and storage resources, right? And the capability is basically to serve the road level devices. Now, we also have cloud servers that are accessible basically for road level system devices that are connected either through the centimeter wave or optionally the millimeter wave. Now, to get back very quickly to the OBUs and the roadside units, what they will be basically communicating, RSUs are basically stationary wireless or wireline communication devices. So they will be collecting traffic data from static sensing or relaying this data further to the MAC level and or the cloud layer, and the mobile and stationary devices, the OBUs, with their available technologies, will be transmitting their own information or their own sensory information using these technologies to the MAC layer or the cloud computing layer. Now, speaking precisely about the communication technologies that are available, we are in PoDIUM using frequency range 1 or FR2, so basically 5G centimeter wave or millimeter wave. So sub-6 and 24 to 26 gigahertz for the millimeter wave optionally, and the ad hoc wireless network communication, which is basically restricted here to local communication, is 802.11 AD. In addition to ITS G5, it's basically known for its broadcast format, as well as sidelink, or also known as PC5. In all of the figures, you see that we also include the wired communication, because for the fixed part, for example, between the RSU and the MEC or into the cloud, at some point the communication is wired. Now, concerning the types of communication that we are focusing on, and as I said at the beginning, we orthogonally define the types of communication to the communication technologies. The types of communications that we look at are either a single connectivity or a multi-connectivity or a hybrid communication. And in this, we basically look at point-to-point communication or point-to-multipoint in terms of devices, for example, broadcast and ITS-G5. And when we talk about single connectivity, we are using a single technology between endpoints. So you see this, for example, here in terms of a vulnerable road user or a shuttle user that is using one certain technology, one single technology. Now, concerning the multi-connectivity, and we have this between devices that can basically use multiple technologies simultaneously. For example, such a connected vehicle or a connected automated vehicle that is able to use, remind you, the type of arrows that you see here, centimeter wave and millimeter wave at the same time, or centimeter wave and 60 gigahertz Wi-Fi ad hoc, also at the same time. And this opens up the ability to schedule messages and data packets over the available communication technologies. So the types of communication that we're talking about here is, in terms of multi-connectivity, the ability to choose which communication technology is the best one to use right now. Or the ability to choose a subset of the available technologies to achieve a certain reliability constraint. Not just reliability, but for example, also availability and redundancy, and using redundancy. Now, hybrid communication, what I mean by that is the classical, and this is also one type of communication we are looking at in PoDIUM, that is always duplicating messages. So we simultaneously transmit all available, overall available communication technologies, and trading in the reliability for basically a lower throughput. Now, this redundancy is basically at this point decoupled from the message-specific criticality. So if you contrast this to the multi-connectivity, you see that using a concept of multi-connectivity, you can tag messages with a certain criticality, and hence reduce the latency for certain messages while not for all of them. Looking at the time, I will go over to the last slide of my sub-presentation, which is about the granular view, the different types of devices that we have here. So OBUs that I spoke about, and I said in a second, they are deployed at connected vehicles or connected automated vehicles and emergency vehicles. The UEs are the shuttle, for example, in some scenarios, shuttle users or vulnerable road users. We have also these stationary communication devices, for example, such as the traffic lights. And this brings me to the end of this part of the presentation. With that, I think I will just hand over directly to Jorge.
Thank you, Amr. Yeah.
Thank you, Amr. I hope you can see my screen now.
Yes, yes, Jorge.
Okay, thank you. Well, I'm going to talk about two different aspects of the common PoDIUM reference architecture. On the one hand, the functional aspects of this common architecture, and on the other hand, the data flow aspects of it. Both aspects are closely interrelated because we are talking about the exchange of information between the different functional blocks that are interacting within this common architecture. And in this case, I'm going to present each of them in a separate way, but you will detect this relationship between them as I go through the exposition of details. So let's move on to the first block. The first block is about the interactions between different functions and users. On the right side of the slide, you can see the picture that refers to what we have called the functional view. This means is the common high-level architecture for all PoDIUM use cases that shows these interactions between the different functions and users. Each arrow represents the link between two functions or the presence of an exchange of information between them. And the sense of the arrow means from whom to whom this exchange is made in one way or two way. Since it is a common architecture, now each use case is particularizing it based on the functions, users, and requirements considered on each one. There are three large blocks, as Michael said, integrating this functional architecture: the platform services, the road users, and the sensors and actors. Each one includes several types of functions and users, as you can see also see. In the next slide, we are going to go into detail of each of them. First, regarding the main block, the platform services. These are the main functions necessary for the implementation of the PoDIUM use cases. These are the traffic management and/or cooperative maneuver planning. It includes traffic management functions at a strategic level and incorporates the cooperative maneuver planning, which directs vehicles on a microscopic level. Then the digital twin, it is responsible for creating a digital representation of the road network, collecting data from different sources of the road, processing them in the digital layer, and then providing real-time information to optimize traffic. The risk management function that estimates the risks regarding a collision between different road users, the CITS message and user handling, which is the main function to provide connectivity to road users, like connected and automatic vehicles and your use, but also to receive messages from them. Finally, the software integrity function that provides the attestation procedures of OBUs and roadside units to establish their integrity. Regarding the functions related to road users, these are collected into three high-level categories: the connected, conventional, and emerging vehicle functions related to vehicles that are manually driven, and can communicate with the infrastructure by different communication technologies, but also receive information from it by means of an HMI. Also, the connected and automated vehicle functions related to vehicles that drive in autonomous mode and interacting with the infrastructure for the automated driving function. Finally, the vulnerable road usage functions that contain all of which are related to VRU functions. Here we should remark some functions that are common for all road users, like the positioning or the local dynamic map, and some others that are specific, like the automated driving functions for perception, planning, and motion control, or the HMI application and navigation for VRUs. Regarding the sensors and actors functions, we differentiate between the infrastructure-based road user detection function and the traffic lights. The first function analyzes the data collected from sensors installed in the infrastructure to provide advanced detections and perceptions capabilities. We are talking about different sensors for further analysis and cameras, radars, and lidars to detect road users, usually by means of machine learning techniques. And the traffic lights function provides the typical functionalities at control intersections to support traffic management decisions. Now let's move on to the second main block, the data flow, which is quite related to the functional interactions. It is worth mentioning that for this purpose, we are following the X16 standards in this field, mainly the ones developed by the European Telecommunication Standards Institute, ETSI. We are using these standards for the definition of the great majority of messages, but in some cases, as Michael said, we have detected a need of extending the standard because, for example, it doesn't cover specific aspects of the regard functionality. Then we delve more deeply into the semantic interoperability aspects. I mean, trying to answer to questions about the motivation for proposing a deviation from the standard, the possible impact and its severity and mitigation strategy. And finally, in order to have a common picture of all these, the exchanges of information, we elaborated the data view that provides a global picture of the management of information within the PoDIUM architecture, showing the types of messages exchanged by the different functional blocks, and also its use cases, particularizing it based on the interactions between functions considered on each one. So here we have the data view, which includes all blocks and functions that I mentioned before. Since the functional interactions and the data flow are closely related, as you know. It is a complex picture, so I'm trying to explain it using the different messages that are going to be sent and other additional exchanges of information that aren't strictly ETSI messages. First, regarding the ETSI messages, we will send a lot of them, as you will see now. Basically, these are the cooperative awareness messages, namely CAMs, to send the position and speed of connected and automated vehicles to the CITS messages server and to exchange them between different vehicles, and also to send users detections from road sensors to the digital twin. The cooperative perception messages, namely CPMs, to exchange perception information of connected and automated vehicles to the CITS server, and to exchange them between different vehicles, and also to send these perceptions to the digital twin. The decentralized environmental notification messages, namely the DENMS, to send collision risk alerts from the risk estimator to the CITS server, and also to send risk alerts, road hazards, and traffic incidents to vehicles and VRUs. The in-vehicle information messages, namely the eBeams, to send it to them to vehicles. maneuver coordination messages, namely the MCMs, to send cooperative maneuvers recommendations to vehicles and VRUs, and also to exchange them between CITS servers and the digital twin. The vulnerable awareness messages, namely the BAMs, to send VRUs detections and their location and speed to the CITS server and to the digital twin. Then the map extended messages, namely the MAPM, to send information about the road infrastructure controlled by the traffic management service system, the signal phase and timing extended messages, namely the SPATM, to send the status and timing of the traffic lights. And finally, other types of information that are sent without any specific etc message, like the emergency vehicle priority requests, the traffic data, status and plans that are controlled by traffic management system, the information for the shuttle management and app, and the information for the software integrity. And that's all from my side. Thank you. And I give the floor to my colleague Guido.
Thank you, Jorge. See my presentation?
Yes, Guido, we can see it.
Thank you. Okay. Hello, everyone. I was going to talk about the data truthfulness and the software integrity for ITS that we are developing in PoDIUM project. The trust and truthfulness are two concepts that deal with the simple question that is how can automated vehicles and algorithms rely on what the PDI says? That means that information that the data produced by different sensors or road users, how is it reliable? Because sensors might be produce false positives or false negatives, and also the road users' data in the same way. Any user with a radio access can introduce malicious messages into the network and produce false output into the applications. And so the services running on the edge or the cloud services we have will produce false results or invalid results that an automated vehicle cannot rely on. So this question can be split in two questions that address the trust concept and the truthfulness concept. The data, are the data users or sensors really who they are? So can we assess they are a vehicle, they are an authorized user to send messages to our platform? And is the physical and digital infrastructure what the digital infrastructure receives true? So that data produced by sensors is true. So on the first part, the trust concept gives birth to the strategy of the trust computing. This is an existing concept to keep a computing system's integrity. So in a few words, the integrity is the detection of software modifications with respect to the original software that was present on the device during the operation. So a computing base with a trust platform module that we can call an anchor. It's a piece of hardware that is able to perform cryptographic primitives. So in many products exist on TPMs, trust platform modules, and it is used to keep the integrity of the computing basis, to check the operating software and running applications, and it can verify that the system is running the original software. So on the integrity of the architecture of this integrity, approach is that the TPM locally collects the hashes of different components from the very beginning of the system boot. Checks this device checks that the bootloader is the original one and the kernel is the original kernel, certified kernel by the manufacturer, and any other components, software components or applications that are present on the system. We can, for example, say the CCAM service is present, or we should define at the moment in the project which components should be verified. But all of them are hashed and verified by this TPM component. Okay, this occurs locally, but also in the same principle is external to the OBU. So as a trust computing base, the onboard unit has an external attester. So in the network, the attester is in charge of challenging the OBUs for integrity proofs in order to verify their trustworthiness. So verify that all the software is the same original software and it hasn't been changed during the operation, the onboard unit operation. And it will take countermeasures in the case of negative attestation results. Thanks to the multi-connectivity approach of PoDIUM, we can consider that the roadside units being fixed devices in the roadside can be also attestors. But they are also, given that they are placed in public places, they are subject also to potential tampering. So we will protect the roadside units as trust computing bases. So nets in the edge level or even in the cloud, there can be attestors that can challenge either roadside units or the onboard units as a trust computing basis, but the roadside unit can challenge also the onboard units. So we can have a trust computing base, a roadside unit that declares that an onboard unit is verified. So, in brief, an onboard unit is when it's attaching to the network, it will look for a CCAM broker, as C. Rhodes states, and the rest of the interactions with the services will continue with CCAM messages, sending CAM messages or cooperative perception messages, or even DEN messages. Making their way into digital twins and the applications that we are implementing in PoDIUM. But just as the first step, just in the discovery phase, the attester is put in the middle as a requirement to be, the attestation should be positive in order to the onboard unit to be given the proper credentials to start using the CCAM broker. This is after the first attestation, the credentials are generated and given to the onboard unit. And so it can start transmitting and producing messages. But these credentials have a timeout. So because the attestation procedure is periodic, is because the tamper can be in any moment of the onboard unit operation. So during the onboard unit operation, it might be tampered too. So the periodic attestation is required in order to keep the attestation, the onboard unit to be verified continuously. And so the attestation, the credentials have a timeout of validity. On the other side, the truthfulness approach, it answers the information, the question of is the information from applications and algorithms reliable? And that means that the input to this application should be reliable. I mean that all the sensors and the sensors in the roadside or in vehicles or the information provided by users should be reliable. And so the algorithms can produce reliable information suitable for connected automated vehicles to use it, such as in the case of an intersection maneuver assistance in the case of use case for in PoDIUM. For PoDIUM, two strategies are being implemented. One is the self-assessment of the Fusion module, which is implemented by University of Ulm, and it's based on the check of the data, small sets of data, and making statistical assumptions on this data, and being processed by subjective logic. So this allows the applications to validate the behavior of a user to assess it is a pedestrian or a vehicle and make this information more reliable taken from sensors. And the second approach sub-strategy is that the redundancy-based sensor data fusion, which is implemented by Links, it's based on the rank of information in truthfulness levels according to the number of redundant sources. We can see here in the plot that in this drawing that we have many cameras and car sensors and other road sensors that produce data into our digital infrastructure with basically redundant information. So in the next slide, we can see an example. There is a road user, such as a bicycle person on a bicycle, a cyclist, which is detected, for example, with a front camera from a vehicle, and it produces a CPM, um, collective perception, cooperative perception message, and it produces a bicyclist and light VRU vehicle on this message, and it arrives to the platform. Another message from a camera detecting a pedestrian and a cyclist on the same lane. In the same time, a van message arrives from the onboard unit on the bicycle or even on a VRU application on the smartphone, arrives to the platform. And so we can see how the same information is aggregating into the system, and there's a higher probability that a cyclist is present. These are only three examples of the information that can feed on the data fusion on the system, because there can be, we can use also the data of the vehicle that is the position of the vehicle that is taking the CPM, for example, and it rises the probability that the cyclist is certain present on the lane.
Guido,
Yes.
sorry for the interruption. Could you
Mhm.
please come to a conclusion so we have some time?
Yes, I have 2 slides left and I will end. So we can see how the truthfulness grows as the data is growing, as the data is more reliable. And in consequence, the information is also reliable. There is an ITS value for decentralized environmental messages that describes the information quality. So the information quality grows, for example, on a DEN message. And also we can see that the information is a higher probability or a higher quality of being certain, and we can improve the precision in the case of the localization of VRU. So we can say that with these two strategies, the trust and the truthfulness, we can produce these two results: the reliable data from trusted sources, so not only reliable data, but also potentially more precise from verified sources. So services operating on that data will produce higher quality outputs such as DENS or EVIM indications to vehicles. So this is how we address these two concepts. So I'm open for questions when the time is right. Thank you for your attention.
Thank you so much, Guido, and thank you all for your input and presentations. Keeping an eye on the time, I will open the floor for discussion right away. I already have 3 questions. We will be taking this for sure, and then the rest, as Lazarus suggested um, on the chat, we will be glad to answer them offline. So a question to Amr from Gregorio. He noticed on your third slide of your presentation that you saw that the MEC is connected directly with connected vehicles and connected automated vehicles. He's asking how is this so if the ETSI specification has a MEC collocated with a BS, making a direct communication link not possible.
Right. Okay. Thank you, Xavier, and thank you, Gregorio. I'll just be short on the answering this one. So the figure does not show the actual architecture of the mobile network. So at no point in the figure you see the base station actually, but you see the access technology, right? So the communication technology, the centimeter wave or the millimeter wave 5G. Now the way we or I understand the question about the co-location, basically with a base station. To my knowledge, the MEC is access agnostic. So we do not, it's an option, we do not provide here a cellular implemented MEC, but it is one option. So the way we have it here is that we have the MEC not co-located basically with it's not a mobile or a cellular implemented MEC. I hope this answers the question.
Thank you, and of course, offline we can discuss it in more detail. A question to Jorge from Andreas regarding your presentation. Why is the camera sending comes in addition to CPMs? That was the question.
The camera is sending CPMs. Not, I think it's not the cams. You probably didn't understand. I said that the camera is sending CPMs. I'm sorry.
Okay. So this is clear. So just CPMs. And the last question addressed to Guido. This is from Peter Paul. Is usage of EU CCM's trust domain for adding trust to the transmitted messages, which are suitable for 5G, ITS, G5, SL. Are they not considered?
Yes, that's a good question because here in one of the slides I showed, let me show here. Okay, this slide assumes that we have an external authority that handles the user authorization, but we are not considering here in the project, but we assume that this is a new concept being brought into the CCAM world. So we are thinking on the first mechanism to authorize a user or not authorize a user, but leaving the user management outside of this mechanism. On the other side, something that I didn't say before is that the ITS security mechanisms present already on the standards are not enough to protect an onboard unit from tampering, because an onboard unit might be tampered, but continue working as normal with the normal certificates. But if he has been tampered, it can behave differently from with respect to its original software. I don't know if this answers your question, Peter.
Thank you. Guido, for your answer. Let me also give you some useful links. So I guess we got to everyone and the questions. I would just like to ask Lazarus, Michael, if you would like to touch upon anything before we conclude the webinar.
No, I think we are okay to go. Thank you all for attending the meeting, and you will be receiving some content from us soon. Thank you.
Okay. Thank you, Lazarus. Well, thanks a lot to all the great speakers and the audience for being part of today's webinar. You can find an article on the platform architecture on our website, and then the deliverable that has a detailed description will be available soon on our library at the Zenodo community. And yes, stay tuned. Any other questions, we'll be glad to take them offline, and hope to see you in our next webinars. Thank you so much for joining, and have a great rest of your day.
Bye.
Thank
Bye.
you. Bye.
Thank you all. Bye.
Thank you. Bye.